Mm-hmm. So thank you for. Okay. So actually, I can start now, right? And so I think when I sent you the title, it was discrete geometry in convexity spaces, and then I liked better combinatorial geometry, but even that name is not great because it should really be combinatorial convexity in convexity spaces. But then there were two convexities in the same sentence, so I didn't like that. So this is the title, and so basically there's an area in combinatorial geometry which we could call combinatorial convexity, which is motivated by Euclidean convexity, the standard convex sets that you're used to, right? And for a long time, actually, quite a long time, one has tried to, or been interested in putting this on a purely combinatorial ground, these type of results, and that's where these convexity spaces arise, right? So that's sort of a combinatorial model of convexity. And there was activity, I think maybe in the 50s or 60s was when they really started with this, and then up to the 80s, then people gave up because they couldn't solve their big motivating problems. And then around the 1990s and 2000s, new problems arose with standard convex sets, and one started getting hope again. Oh, well, maybe these work in convexity spaces. And somehow the last 10 years, the snowball started rolling a little bit again. And so that's what I kind of want to report on. And it will be mostly a survey. There might be a result or two of mine inside there, but mostly it's a survey. So first thing I want to do is to give you some picture of some of those questions in combinatorial geometry or combinatorial convexity that we would like to extend to this combinatorial setting. And the first theorem, which is a very classical theorem in combinatorial convexity, is Tverberg's theorem, which is a classical result from 1966. And there's some very sad news that goes with this, which is that Tverberg passed away 2 weeks ago. And so that I got this news about a week ago or so. So that's especially sad for me because he was my advisor. But we move on. We celebrate his most famous result, which is this one, which is really considered a gem in combinatorial geometry. A very beautiful result, which says the following. So you take a set of points in the d-dimensional space, right? And suppose the number of points is this specific number here. So dimension plus 1, k minus 1. K should be an integer at least 2, and then you add 1. Okay? And if you take this many points or more, but focus on the equality here, then you can split those points into k parts, such that the convex hulls of each part will intersect. Okay? And the simplest case is when k equals 2. And here I just picture the dimension 2, since that's easiest to draw. So when d is 2 and k is 2, it means we have 4 points. And apart from some degenerate cases where you have points that are collinear or something like this, 3 points or more collinear, these are the 2 cases that can occur with 4 points in the plane. And you see either the 4 of them, the convex hull forms a triangle, in which case that will be one part, and the point inside is the second part. Other case, the 4 points are in convex position, then you take the diagonals of the quadrilateral they span, and their convex hulls intersect at this point here. And so for the case k equals 2 and any dimension, this is an old result from 1921 called Rodon's lemma, which he used to prove another classical theorem in convexity called Heli's theorem. Right? So that was well known, and Tverberg's famous paper from 1966, the title is A Generalization of Rodon's Lemma, and contains this result, which is for all d and k, right? And here's an illustration of the case d equals 2 again, and k equals 3. And already here, it's not completely trivial to prove, and in general, this is not a trivial result for arbitrary dimensions. So here we see I have 7 points. I take these 3 forming a triangle, this segment, and all the convex sets that you form by this partition will have a non-empty intersection. Another thing that we should note is that you might ask, well, what is this number best possible? What if I remove that one? Right? That's an obvious first question. And then it becomes obviously false. Right? And you might want to try to think about that. Imagine you took 6 points in the plane. Maybe you want to split them into pairs. So a pair and a pair and a pair. Each pair will span a line. But in general, 3 arbitrary lines, will not intersect in any point, right? So not only will not the convex holes intersect, in general, the linear holes don't even intersect, right? So really, and this same argument can work in any dimension. So really, that is the precise number for which this splitting happens. And this is a celebrated result for many reasons. First of all, it's simple to state, quite beautiful. It's not trivial to prove. His original proof was considered very, very complicated. Short, but complicated. And since then, I think there are like 5 or 6 proofs, and now there is one particular proof by Zakaria that was discovered in the 90s that is quite simple, but it's sort of ingenious, using some tensors and things like this. And it's not something you would not come up with this proof. And I mean, it took 30 years for Zakaria to come up with this proof, right? And this is a celebrated theorem that a lot of people have been interested in. So even though there is sort of a relatively simple proof now, it's not something obvious. It's obvious that it should be true, but it's not obvious how to prove it. And there are many applications. Tverberg originally wanted to prove this. One of his motivations was to prove something called the center point theorem, which says that if you take n points, so imagine a large points cloud, right? And then for every, let's take in the plane, large set of points in the plane, and take the convex hull of any 2/3 of the points. Right, so for every 2/3 of the points, you take the convex hull, you get some convex set. And do this everywhere. Then there is a point that intersects all of those points, and he could use this to prove that. A point that intersects all the sets, and he could use this to prove that. There are many other proofs. That's one application, and since there's been numerous applications, and another reason that this is such a celebrated theorem is that it spawned off a huge number of proposed generalizations and things like this. There's a huge, huge literature about generalizations and variations of this result. And so to celebrate Tverberg, I thought originally I wasn't going to include this, but to celebrate him, I'll discuss some of those generalizations. Why not? They're also so nice. The first one, okay, so this is really about points in the Euclidean space and splitting them and taking convex hulls. That's what this is about. And the first generalization is here due to Borony. He became interested in Tverberg's theorem in the 70s, and he made some conjectures, and eventually in 1981, he could prove this theorem, which is known now as the topological Tverberg theorem. So here, K is, again, going to play the role of the number of parts, but we're going to require that K is a prime number. Okay? And set n equals dimension plus 1 times K minus 1. That's capital N. Now take any continuous map from, and this is the n-dimensional simplex, so that has n plus 1 points. So there's n plus 1, that's the Tverberg number, right? So the simplex spanned on n plus 1 points, and you map by any continuous map into the d-dimensional space. then you can split this simplex into k disjoint faces whose image intersect. Okay, so maybe here I can start using the blackboard. Okay, so when I took the convex hull, let's do k equals 2 and d equals 2. So in the convex case, it meant I had 4 points like this. I split here and I split here, and I had this common intersection. But what the topological Tverberg theorem is saying is that actually it doesn't matter that you're taking the convex hull. Imagine now you take the three-dimensional simplex with 4 vertices, you map it continuously into the plane by any continuous map you want. Maybe this pair, the edge connecting those two gets mapped to this guy, but the edge connecting these goes like this, right? And the edge that connects these, maybe like this. Edge connecting this pair maybe goes like this. But now I think I found my partition. So the face that was spanned by these 3 vertices somehow gets mapped to this region here, and the vertex, the remaining vertex, gets mapped to here. And so the image of that triangular face by these 3 points will intersect this 0-dimensional face, the image of this 0-dimensional face.
So the triangular face could be the outer face?
No. But there could be holes, and you might have to be careful about this case. But yes, I mean, it's a continuous image of a compact set. It will be compact. It's not going to be the outer thing. But there could be holes, right? That triangle face could wrap and make some kind of holes. And yeah, many things could happen. But nevertheless, this is true. And that was for k equals 2. And it works when k is a prime number. And you might wonder, why would a prime number arise here? That seems bizarre, right? The reason is this kind of proof of this theorem relies on certain tools from equivariant topology. And so you have these equivariant spaces with a group action on it. And this group action, usually for these kind of fixed point theorem type things, these group actions must be free. And that's where, long story short, that's where the prime power comes in, is that if the group action is a ZP action for some prime, usually this action will be a free action, and that's when you can start using these topological tools. So it's sort of natural that prime numbers arise, and it was even extended to the case when k is a prime power, so the power of some prime. Several people did this. And one of the long-standing conjectures about Tverberg's theorem was that it should work, was whether this is true for any integer k. And very surprisingly, to many of us, but to some maybe not, it actually fails when k is not a prime number. Sorry, prime power. So based on some work by Mabillard and Wagner, Florian Frick managed to construct counterexamples, and in fact, so for any composite number, so sorry, non-prime power, he can find a dimension for which that statement will fail. And there's still some question of how small dimension can you make the counterexample. And for example, in the plane, no known counterexample is known. And in the plane, it really becomes kind of a graph drawing problem. And people still believe that in the plane, the topological Tverberg should hold. All right, so basically, in the plane, when you have this continuous map, your triangles kind of look a little distorted like this, right? And here might be a case where you have a hole, for example. Maybe, I don't know. But there are reformulations of the planar version as a graph drawing problem. And this is still open and maybe believed to be true. But it was maybe around the early, let's say 2010s, that some people working in topology started suspecting that this is going to fail. Didn't know how to make the counterexample, but there were sort of suspicions that maybe it's not going to be true. There are famous names involved here, people that thought about that. For example, Gromov has always said that, no, this is not going to be true for non-prime powers. And it turns out that that was, in fact, the case. So that is the topological Tverberg theorem, and kind of from 2015 concludes sort of a long story about this, which was initiated by Barney's interpretation of Tverberg's theorem. Yeah. Okay, that's a very good question, and there's current work on those things, especially by Frick and Soberon have recent results saying that, well, okay, that number isn't going to work, but increase n a bit. When does it start working, right? And so, a very natural question, and that is, topic of current research. Okay, one more extension. It's called the colored Tverberg problem. Yeah. And this is, well, you see, Barney's name is a lot involved here. He was one of the big fans of, or is one of the big fans of Tverberg's theorem. So they came up with this conjecture, and they proved the planar case in '92. And there was a very specific reason. They were working on a problem. They realized, wow, we needed what we call a colored version of Tverberg's theorem. So here, instead of a single point set, I now have d plus 1 point sets, each one of equal cardinality. Right? So finite sets. Then you can make a partition of the union of them into k parts. So k is the size of each of these sets, such that the convex hull of the k parts intersect. But what's important here is that each of these parts picks up 1 point from each of these sets. Okay, so imagine these are sets of d plus 1 different colors, right? And you're splitting this union into d plus 1 tuples that are colorful, 1 point of every color. You take these convex hulls, and those convex hulls should intersect. That is the colored Tverberg problem. Is this always true? Right? Okay, so there's a reason this problem arose, which is combinatorial. So in discrete geometry, we have huge points of sets. We want to partition them and find structure there, right? And if I want to apply the original Tverberg theorem, suppose for some reason I want to split into parts that convex hulls intersect, right? And if I go back to the original Tverberg theorem, what is sort of the configuration space of partitions I'm looking over? Well, it's all possible partitions of d plus 1 tuples. Let's just say we take d plus 1 times k for simplicity, right? So it's all possible. It means I'm looking at the complete d plus 1 uniform hypergraph, and I'm looking at all possible matchings in there, right? And to find d plus 1 complete d plus 1 uniform hypergraph, it requires, so to find a structure to apply this to, you need to apply Ramsey theorem somehow to get something complete. But, oops, wrong way. But to find a situation where you have the configuration space here is a multipartite structure. And those arise by supersaturation very quickly. As long as you have a dense hypergraph, there's going to be a bunch of these, and you can start applying colored Tverberg every time you see one of these. So there's some kind of combinatorial reason why this is a much more applicable result. And it indeed has a lot of applications. That's a kind of vague explanation, but you can stop me and ask for details if you want to know more. Okay, so here's an example. 3 red points, 3 green points, 3 blue points, and there's a colorful partition. And this theorem is known in the plane. Then in the plane, this is a theorem. That was what Barney and Larman originally proved, and they could use this for something. And then very recently, 2015, that might be the publication date. I think the result was proven in 2010 or something like this. But for any dimension, but the number of parts plus 1 should be a prime. And again, it has to do with this equivariant topology. So they use some sophisticated tools called equivariant obstruction theory to prove this. And again, these prime numbers pop up. But much more recently, or more recently than this, Frick, and so Frick was a student of Ziegler and Blagojevich, he was the one who discovered the counterexample to this topological Tverberg. He also found a way, or they found a way, to prove these known cases. So this original proof, very complicated, using very heavy tools from equivariant topology, but they managed to deduce it from here. So there's some kind of technique or trick to deduce the colorful version from this one using more elementary tools, let's say elementary tools from topology. Yeah, so this is a wide open problem to do this in general, I think. All right, so already for what's dimension 3 and 3 parts is open, right? I mean, this must be possible to solve, I think, but yeah. And here, I don't think we are sure whether this is really a necessary condition. It's really something that arises in the proof that we need prime numbers in. Okay, so, yeah. No, not even known. Yeah, good question. So not even known for prime power, as far as I know. Yeah. So.
But you said it's for
no.
general, right?
This? No. No, this is wide open in general. Because so the thing is, actually, so what they prove here, they prove a continuous version. So just like I have the continuous version of Tverberg's theorem, instead of taking convex hull, you have the images of these continuous maps. Their proof gives you the same, where you're taking the continuous image of this hypergraph form, this complete multipartite hypergraph, right?
But also true for
Frick's proof also relies on this, I believe. Was there something? Oh. Okay, or learn more, or okay. Yeah. But my belief is that there should be some geometric method to maybe approach this, right? Where with the convex hulls, like Tverberg's theorem for convex hulls holds for all numbers k, right? And as soon as you go into the topological setting, that's where these prime numbers pop up. And my belief is somehow that, forget about the topological general case, just think about convex hulls. And
but these cases hold the topological.
the known cases hold in the topological setting, that's right. Yeah. And this is also the deficiency, that's why the prime numbers pop up, and that's they don't know how to get rid of this. Yeah. Okay, so that was some background on this classical problem in combinatorial geometry or combinatorial convexity. And now I'll introduce this thing called the convexity space. And this is a very general structure. It's a hypergraph. X is the ground set, and C are the edges or the sets. It's a set system. And there's some very simple axioms. First of all, C should contain the empty set and the full set. C should be closed under intersections. So you intersect any of the sets, what the resulting thing should be in your family in C. And it should be closed under nested unions. That third axiom I actually never bother with, because the convexity spaces I like are finite, and then this last axiom doesn't really gives itself. Right? This is kind of a topological compactness kind of condition. So if you're only interested where C is a finite set or finite family, then this gives itself. So then you see it's a very general system, a very general set system, simply closed under intersection. We call the members of that family, we call them convex sets. Right? And once you have this, you can define the convex hull, take any subset of the ground set, then you intersect all the members of your family that contain that set, and that is the convex hull. So that's basically just the smallest set in C that contains Y. Okay? And this is a convexity space. And maybe we should try to think of some examples. Simplest example is just take C is the power set. Yeah. That's sort of similar to when in topology you take the trivial topology or something like this. Right? I think the closed sets in a topological space form a convexity space. Take a group and look at all the subgroups, and maybe remove the identity element. And in many of these examples, I tell you now, maybe you trivially have to add empty set in X, but that's easy to do, right? So take all the subgroups of a group.
Closed set and finite.
Yeah, maybe.
What is nested?
So,
Yeah.
like this.
Oh, I see.
So for finite things, it's
Yeah, exactly.
One is a subset of another.
if you have a biggest
You have a system like S1, S2,
like
then the union of, yeah, exactly. But personally, I only think about the finite set system, and then I don't consider that one at all. Yeah, so subgroups of a group. There were many. If you have a metric space, you can define geodesic convexity. So you have the shortest path connecting 2 points, and you just add all of these. It forms a convexity space. Lattice convexity is you take the integer lattice, and then you look at standard convex sets like this, and those subsets that can be cut out by a convex set, those are convex. Right? They're closed on the intersection. All of these are examples of convexity space. In fact, the notion is so general that you can take anything you want and turn it into convexity space. Right? It's kind of meaningless, right? Take your favorite set system and just close it by intersection. And as long as so if you started with a finite set system, then you're fine, right? Or else you maybe have to worry about this one. But yeah, any set system gives you a convexity space. Just close it by intersection. So super general, and you might wonder, can you say anything at all? Well, there is something you can say. But first, we need to define some invariants. And here is the key invariant. So the Rodon number, I'll denote this by R and a small sub 2. This is the smallest integer R, such that if you take that many points or more, then you can split that set into 2 parts so that the convex holes intersect. Okay, so just as in Rodon's lemma. Right? Rodon's lemma is simply saying that, so if I look at the convexity space, what's ground set? RD and CD, that's usually the convex sets in d-dimensional space. So the Rodon number of this equals d plus 2. And that was precisely Rodon's original lemma. Yeah.
If you're wondering what the convex holes are.
Yeah. The convex hole is the smallest set. The convex hole of a subset Y is the smallest set in your family that contains this. In other words, intersection of all the.
Right.
Yeah. So that's a really good question. That's the whole reason this works, is that you can define a convex hole.
Right.
You're closed by intersections. Therefore, you can take the smallest guy that contains the subset. You can define the convex hole, and therefore this makes sense, right? So as soon as you have the convex hole operation, some people call it closure operator. Some people call it closure systems and the closure operator. So as soon as you have that, you can define the Rodon number. And as soon as you define the Rodon number, splitting into 2 parts, why not split into more parts? You get the kth partition number. I should have written, some people call it the kth Tverberg number. I should also be one of those people, but yeah. Anyway, right? So then you can say what is the smallest number so that you can split into k parts whose convex holes intersect. Right? And that is one of the classical invariants of a convexity space. Another invariant is something called a Heli number. This is H of XC. I'll just say in words what this is. it's the smallest number, so that if you take a finite family of convex sets and every h of them intersect, then all the sets intersect. Right? And a very basic lemma or theorem by Levy is that the Heli number of a convexity space is always strictly less than the Rodon number of the convexity space. So for example, in standard convexity, the Rodon number is d plus 1, the Heli number is, sorry, the Rodon number is d plus 2, the Heli number is d plus 1. Yeah. And the proof of this is, I'm not going to give it, but it's completely trivial. So I told you Rodon developed his lemma to prove Heli's theorem. And then you just go into that proof and you delete RD and you write convexity space. And you follow the same proof. And that's it, right? It's really just, it's the same proof, which I'm not going to give you, okay? But it's kind of one of the motivating reasons for these invariants and these things. Right? And it's very similar to maybe matroid theory or something like this, where you try to abstract this geometric situation of vector spaces, right? And you take certain things as axioms or invariants, like here, and things start rolling. And so, of course, one of the major problems, and maybe the major problem in this convexity space theory, was what is the relationship between R2 and RK, right? And that was the subject of one of the big problems in the area, and another attempt to generalize Tverberg's theorem, which was called the partition conjecture, that for any convexity space, the kth Tverberg number is bounded by the Rodon number minus 1 times parts minus 1 plus 1. Right? And if you were to put that into the Euclidean convexity, you see Rodon number is d plus 2, so that's d plus 1 times k minus 1 plus 1. That's Tverberg's theorem. And so this was sort of considered one of the holy grails, because this would give you a purely combinatorial reason why Tverberg's theorem is true. And sort of telling you that it has nothing to do with the geometry of RD or anything like this. Just purely combinatorial fact. And there's a very simple fact that you can bound RK by R2 to the log K. That's not hard to show. And there are a whole huge literature with partial results on this conjecture. Basically, they take their favorite convexity space and they prove it there, right? And somehow all of those examples, I would say, are somehow geometrically motivated, like the lattice convexity. Another convexity space that people like is in RD, you take points, and the convex hull is the smallest axis parallel box that contains them. I think for this called box convexity, it's true, and verified for a bunch of convexity spaces. Then Tverberg, Tverberg and Duché and others later results were sort of reductions. And I think most significant was Duché, who proved that this conjecture is true if and only if it's true in geodesic convexity in graphs. So that's kind of interesting, right? So, and so I think from the 90s and so on, they started making such reductions, maybe in hope of finding a counterexample. But still, geodesic convexity in graphs, it's very geometric. And it wasn't until Boris' book in 2010 constructed a counterexample, which I would say is very non-geometric. So he found a counterexample, and I'm not going to give it to you. I'm going to mention what is the main tool, the idea. So also he proved an improved bound on the kth Tverberg number, namely the kth Tverberg number is some constant times k squared, roughly. Right? It's bounded by this. And he suspected that actually this should be bounded by a linear function in k. So this he mentions in his paper. Another very famous thing about Boris's manuscript is that it was never published. So, and now me and several others are always talking about this as Boris's famous unpublished paper, and he likes it so much he says he will never publish it. So you find it on archive, but the reason it never got published is that it took the referees a long time to verify. In fact, some referees maybe never believed that it was correct, and because it's written in some very complicated way. But with a former student, Dongyu, we actually went through it and simplified it, and it is correct, 100% sure. And many people did believe it, though, but there were some people who didn't believe it. And so, no, maybe we will one day. So I discussed it with him, and he says, yeah, please go ahead and do it. But he's not my student anymore, so it means I'm the one who has to write this all up, and maybe someday. But maybe also just put it on archive at least. So there are people who still doubt his construction, and there are typos in his construction, and it's very complicated. And that's why it was very difficult to verify in the beginning. Yeah. But the reason that people could not disprove it until Boris is they were thinking about these convexity spaces in very geometric terms. Like I said, in terms of geodesic convexity or this box convexity or something like this. But what Boris implicitly does is it constructs a completely different convexity space. So what you start with is a simplicial complex. Okay, so that's a finite set system closed under subsets. Okay? And then your ground set X, this is the set of facets of K. Right? So these are all the maximal sets in your simplicial complex. And you defined the convex sets, the following: S sigma is in K, so sigma is a face in K. So for each face you define a set, and this is S sigma equals those tau, the facets such that tau is in sigma is in tau. There we go. Okay, so I have a simplicial complex set system, right? And I have the maximal sets on top. That's my ground set. And for every face in my simplicial complex, I just look at all the facets that contain that set. And that's a convex set. And it's very easy to verify that this is closed under intersection. Okay? And this is the type of convexity space he works with when he defines his counterexample. Oops. Oh. Did I make... yeah, that's probably... Sigma, but there says sigma in sigma. That tau is on top, and sigma is a subset. Yeah. Yeah. Thank you. Right. So just think of the simplicial complex as this poset or lattice, right? And so for every face, you just look at everything. You look at the guys here that contain. Right? That is your convexity space. And so this way you can construct a huge number of convexity spaces, right? And really it's purely combinatorially defined. And then once he sets this up, say prove that this is a convexity space, well then you just need to choose K very carefully, which I'm not going to explain, right? But he selects K carefully, and then he can construct, a convexity space where R2 equals 4, but RK is at least 3, K minus 1 plus 2. So it's just barely a counterexample. It's 1 point away. And that's somehow the best he could do. But who knows, maybe once we do write up sort of the simplified version of his construction, it could be possible to go into this and see if you can stretch it further out. So really he only could get 1 point away from here. And he conjectured that really Rk should be bounded by some linear function in K, where the constant, of course, would depend on the Rodon number. Okay, so that was the end of this Tverberg theorem part. And I think all of this stuff indicates, so these are negative results, and the topological Tverberg is negative. And what I think it emphasizes is that the original Tverberg theorem is quite remarkable, right? That's the one that holds in all cases. Okay, so now I'll move on to a more recent result from combinatorial convexity due to Alon-Kleitman. And also a very old conjecture, conjectured in the 50s by Hadwiger and de Brunner. And it's dealing with what's called the PQ property. So the PQ property is I have a family of sets, and suppose among any P of them, whenever you take P of the sets, some Q of them intersect. Okay, that's called the PQ property. And what Alon-Kleitman proved is that if F is a finite family of convex sets in the d-dimensional space, they have the PQ property where P is greater or equal to Q, is greater or equal to D plus 1, then the transversal number of the family is bounded, which means you can find a finite number of points, whatever this number is, and you can pierce all the sets in your family by that number of points. Okay? So this is completely independent of how large the family is or anything. As long as among any P some Q intersect, you can pierce by this finite number of points. And this determining bounds on this number is a major problem in discrete geometry. To try to understand what this, how this function grows. Some special cases, if you put P equals Q equals D plus 1, that is precisely Heli's theorem. And in that case, it's 1, right? So among any D plus 1, they intersect, then they all intersect. You can pierce by 1 point. And then you have here some bounds how this function grows, or what we know. You see the upper bound and lower bound quite far apart. The only exact case that is known, apart from this P equals Q equals D plus 1, is if you satisfy in addition these bounds, then we know this number. And, oh, yeah, I see now. This was reduced. 13 was reduced by someone recently. 9? Okay. I didn't update my slide. So, okay. I'll confess, this slide was stolen from an earlier talk. Yeah. No.
Just this slide.
Yeah, just this slide. So that was, yeah, that is my mistake. A student of Shira, I think, did this, right? Yeah. Reduce this number to 9. Okay. As far as I remember, I read this paper, and I remember they even offered money prize for how much you could improve on their bounds. So you should be getting something in the mail, right? Yeah. Okay. So this is a very also famous and celebrated result. Much more.
We had a comment in the live chat from Hong. He says the linear bound that the conjectures has recently been confirmed.
Oh, really? Oh, yeah, okay. That's true, because I was going to mention that later. It's Domator. I know who did that, yeah.
Sorry.
No, that's fine, that's fine. No, it's good, because I'm running out of time. I might not even get to it. But, okay, so anyway, a lot of effort also is interested in trying to extend this to more general set systems than just convex sets. And a natural setting is the convexity spaces. And a lot of questions were raised about that. But in general, one reason I want to motivate, why do we want to have this more general than convex sets? Okay, so here is an example. Take, for example, a graph. G is a finite graph. Okay, and look at the independence complex. Okay, so that means the simplicial complex whose faces are the independent sets in the graph. then plug it into Boris's machinery, you get a convexity space. So this complex gives you a convexity space. Okay? And it's not hard to show that. And now in that convexity space, let me look at a specific family, F, which is the subfamily SV. So the convex sets that are above every vertex, right? And it's not hard to show that the transversal number of this family is equal to the chromatic number of the graph. This is not hard to see. And, well, moreover, if the clique number of G is, let's say, at most P, then the family F has the P2 property. So in other words, if you're proving for this convexity space arising from this independence complex, you're proving a PQ theorem there, you're proving chi-boundedness of that graph. Okay, so there's a relationship here between a different branch, especially studied in graph theory, which makes this very relevant. And that's why we want to understand this as an abstract way as possible. Okay. And okay, maybe I'm going to speed up a little bit. So one of the things that was discovered is that if your convexity space has something called the fractional Heli property. And let me see if I can describe what this is. So there's K is an integer, alpha and beta are numbers between 0 and 1, real numbers. So you say that the space has this fractional Heli property if for every finite subfamily that F should have been a G. I see now. So what does this say? This notation is from the F vector. So I'll say in words. So take your finite family, F or G or whatever you want to call it, right? And suppose an alpha fraction of the K tuples intersect. Then you want to say that a beta fraction of the members intersect. Okay? This is called the fractional Heli property. And what Alon-Kleitman, Matuszek, and Meshulam showed in a very nice paper that also includes, something close to this construction here. They say that if your convexity space has this fractional Heli property, then you have the following. It implies another property, which we call the weak epsilon net property, which says that the transversal number of your family is bounded by a function of the fractional transversal number. Okay? And so this is very significant result, because this kind of implication here, the transversal number, you're solving an integer linear program. Here you're solving a standard linear program, right? And it's saying that you can approximate the solution to the integer linear program by some function of the rational one, right? And so in a convexity space that has this kind of complicated fractional Heli property, you will have this setting here. Now, of course, the C1 and the C2, it's going to depend on the various parameters inside here. Okay? And then if you know the sort of story about this PQ theorem, you can show that this implies that you get a PQ theorem as well for those convexity spaces. And maybe finally, I can mention the result that I proved with Dongyu Lee. And so what we showed is that if your convexity space has a bounded Rodel number, then so there's a T here. There's this, a KT and a beta T, some function like this, so that if your convexity space has Rodel number bounded by this, then you do have the fractional Heli property for all values of alpha. Right? And this was actually conjectured, or a problem asked by Kalai. And so that solved that. of course, it means if the convexity space has a bounded Rodel number, then you get a bounded fractional Heli number. Therefore, by the previous slide, you have this weak epsilon net property, or this approximation property by the integer linear program approximated by the rational one. That was actually asked by Book in his same unpublished paper. So that implies that. It gives you the PQ theorem, and there was the comment. Domater showed that, actually, Domater used this result to show that the Tverberg numbers grow linearly. That was very surprising to me that he could do this. So, some kind of a circle there. So maybe I have a few more slides, but I wanted to show maybe the key step in how we prove this result. And the key step is to prove something called a colorful Heli theorem. Okay? And what is a colorful Heli theorem? So I'll state what it is. So I'll just do it by an example. So suppose I have a convexity space, XC. And let's suppose that the Rodel number, for simplicity, let's say the Rodel number is 4. Okay? It means the Heli number, and let's assume the Heli number, which is less than this, is 3. So when I take a family of convex sets, any 3 intersect, they all intersect. Right? And 3, since this number 3 here, I'm going to be interested in the third Tverberg number. And let's suppose this is 7, just like it is in Tverberg's original theorem. So I'm just modeling the planar D equals 2 in the standard convexity. But anyway, as soon as you bound this by T, it means the Heli number is bounded, and it also means that this is bounded. Right? But now I just put in numbers, for example. Right? But as soon as you bound R2, then you bounded everything. Okay, so here is the theorem. In this setting, so consider F1, F2, F301 families of sets of convex sets in my space. Okay? And suppose that for every choice S1 in F1, S301 in F301, so whenever I choose a set from each of these, the intersection is not empty. Okay? Then one of the Fi has non-empty intersection. Okay? So I have all these families. These are the different colors. Here I needed 301 colors. And whenever I take sets of different color, their intersection should be non-empty. Then one of these families, all the sets in one of the families will be intersecting. Right? And that's sort of the main step to prove this. And the reason I put these numbers, which correspond to the standard convexity in the plane, is this was already, in standard convexity, this was a known theorem due to Lovász and Barney, called the colored Heli theorem, in which case, in standard convexity, you only need D plus 1 families. But for us, in an abstract convexity space, we need to go all the way up to 301 colors. Does anyone know what 301 is? Where does that number come from? One plus 300, yeah. So maybe the last. Okay, so here I'll give you the proof. So this is the last step. So let's suppose, for simplicity, let's suppose each family has at least 3 sets. If it doesn't, you can make some dummy copies. Doesn't matter. Okay? And for contradiction, let's assume that each family has empty intersection. So suppose it's not true. So then by Heli's theorem, it means from each of these, I can find 3 sets whose intersection is empty. Right? So I'm going to take from F1, I'm going to take, let's say, A11, A21, A31. and so on. Fi, I take A1I, A2I, A3I, right? And the intersection of these three is empty, the answer is these three, so on. If the theorem is not true, this can be done, right? Okay, now I'm going to make a kind of strange table. So it's going to be a table that has height, number of rows is going to be 7, and that's that number there. 7, like this. Okay, and in the first row, I'm going to take, so imagine the set 7, imagine you write this into 3 parts. So let's say 1, 2, 3, union 4, 5, union 6, 7, like this, okay? What I'm going to do is, in this table, I'm going to write A11, 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 so that's this, and then A21, A21, then A31, A31, like this. And then in the second family, I'm going to take a different partition, and I'm going to write in the sets according to that partition. All right, so for example, 1, 5, 2, 6, and then what's left? Whoops. 3, 4, 7. Yeah. So here I will put A12 and A12, and then A22. Like this, okay? And then I continue going over all possible partitions of 7. And it turns out, at least I looked up on Wikipedia, the number of such partitions is 301. It's called the Stirling numbers of the second kind. Okay. Now look at a row. All of those sets intersect, right? That's my assumption. So it means there is a point P1 that's inside all of these sets here. Right? This is the colorful intersection property. Similarly, there's a point P2, P3, P7. Right? So Pi is inside the intersection of all the sets in row I. But the Tverberg number was assumed to be 7. So these guys have a Tverberg partition. The convex hull of these maybe intersects the convex hull of these, which intersects the convex hull of these. And that partition is somewhere in my table. Right? And so it means this was in A1x, A1x. This is in A2x, A2x, 2x, and A3x, A3x. Like this, right? But the convex hull of these is inside here. These are convex, this is the same convex set, so it contains the whole convex hull of these. But there's a point in the convex hull of this, in the convex hull of this, and convex hull of this. So it's inside all of these sets here. But that's all 3 sets in that family. So that triple was actually intersecting, contrary to the assumption. Yes? Yeah. And then you have a colorful Heli theorem. And you see these numbers become enormous if you look up how the Stirling numbers grow. But it seems that you need quite many families to get this colorful Heli theorem in general. And so the standard convexity in Euclidean space is very, very special, is what this shows. Okay, and so then once you have this colorful Heli result, then you plug this into some extremal combinatorics and some kind of thing about dense hypergraphs and blah, 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 you get the result. I won't go through that. And there were a few things to say, but I think I'll end here. There's a picture from Switzerland in 2001, me and my advisor. Yeah, okay.
Thank you. Any questions?
So what is the lower bound on the
Number.
So in the case case when the Heli number is 2 plus arbitrary Rado number, then this construction actually seems pretty close, maybe within constant factor of the truth. But we didn't investigate what happens when you're dealing with higher Heli numbers. Yeah.
So you mentioned now that there's this linear dependence on K for the K partition number.
Oh yeah, okay. Yeah.
Yes. So what sort of dependence on R2 on the radio number?
I don't think it's been computed. So he just uses our result as a black box. Okay, and so it means he somehow needs to play with this function here.
Right.
And this function is
Right.
horrendous, and this function gets worse the larger this k gets. So when t gets large, then this k gets large, and this k gets large because of this Stirling number thing. And
But this K is different from the other K.
This is, you're right. This is not the partition thing. This is, that was maybe a poor choice. Yeah, that's not the same one. Yeah. So yeah, you're right. So he gets C. He gets something like RK is almost C times R2. But this C is going to be. This is going to depend on R2.
C times K.
Times K. Yeah. And this is going to.
Right.
An enormous tower. I don't even dare to think about it.
Oh, okay.
What was it? That's for my paper. Yeah.
That's it.
That's for my paper. Yeah. Yes, that's right. So there's some R2 star 2 star 2 something, but then you also somewhere this Stirling number comes in and amplifies things even more. So it's not really practical. Even though it implies, for example, this approximation of the linear program, integer linear program by the fractional one, that function that you're approximating is so enormous that it doesn't really have any practical application or meaning. No practical application at least.
Your table argument reminds me of diagonalization.
Yeah.
But in a finite
Yeah.
setting. So this is not pigeonhole. This is really more like how would you characterize it? Finite diagonalization argument.
You're right. It's not pigeonhole, but is it diagonalization? So. I'm not sure how to answer your question, but you see, you need to have all the possible partitions, because I don't know what partition this is going to give you, right? So that's why I'm sort of exhausting them all. Maybe there's a way to improve there. I don't know yet.
Any other questions?
So that you get optimal dependency between beta t instead of alpha.
This dependency?
Right.
So what is your question? Do I know the optimal?
Yeah.
No, I don't know. So in the case of standard convexity, the optimal is not. And maybe a handful of other convexity spaces, but in this general one, no, we're losing so much along the way.
Any other questions? Let's thank the speakers.
Thank you.